talk about this work, which is actually using CLIP for medical anomaly detection. This is a joint work with Mashid Shiri and Shidem Beyan. So let me, in a way, this is a data line representation. I try to stay on the times and also to explain maybe the experiments which are interesting. But anyway, I would like to explain first of all the method per se. Okay, so a bit of context first. What is a medical anomaly detection? So as an anomaly, the normal medical anomaly detection, this task consists in the identification of unusual patterns, abnormal patterns in medical data, whatever medical data, especially imaging in this case. Of course, this is a challenging task for several reasons. So first of all, there are a variability of the medical imaging modalities and also anatomical regions. So we have MRI, magnetic resonance, we have histopathological images, we have OCT, we have X-ray, a lot of modalities, and also very different pathological regions like brain, heart, liver, whatever. So the other important issue is about the inconsistent behavior of the anomalies, in the sense that there is not a typical or similar definition for an anomaly, depending on, again, from the anatomical part and the modality. And first of all, there is also a problem of data scarcity, because normally we have to come with a few or zero-shot methods, let's say. And just concerning this latter point, of course, we expected to have these anomalies, which typically are related to diseases which are very few with respect to the normality of the cases. And of course, there is also some problems of privacy and also expert labeling, because the doctors are typically, anyway, useful for taking care of the patient and not for label images. And this also clinical impact. We want to detect early the anomalies so that we can make a treatment beforehand. Resource efficiency, so we have to avoid the annotation cost. So if we have to annotate just a few samples, is much better. And also problem of scalability of over different hospitals, and accessibility in case we don't have a big GPU farm to process the data. So in this context, we propose this MedClip, which is a few shot learning framework for medical image anomaly declassification and detection. So this means also we segment the anomaly in some cases. We leverage on the CLIP models, which I know we are, or most of you are expert on this or knowledgeable, let's say. And unlike the state-of-the-art methods, what we are introducing in this work is an architecture, which is a dual branch adapted architecture and learnable text prompt. Okay, so in this context, let me just give a very short introduction to the state-of-the-art. State-of-the-art is typically subdivided in a supervised method. A supervised method are essentially considering just normal samples, not abnormal data. And the abnormality is just a deviation from the normal, let's say, normal distribution of the data. Normal not in sense of Gaussian, but in sense of normal data. And this is these methods this type of methods are in a way resorting about reconstruction or generative adversarial network for reconstruction of this. The supervised method instead are leveraging on a few samples which are either normal or abnormal, so both normal and abnormal, and also using synthetically generated anomalies in order to find better boundaries between these two distributions, normal and abnormal. And after that, there are clip-based methods. So we inserted the people introduced the language, and mainly there are also a lot of methods in this context. And these methods essentially are using visual adapters to fine-tune clip. Clip is, as you know, pre-trained over a lot of images, natural images, so nothing about medical. And so one of the ideas was to use visual adapters and trying to use some handcrafted or engineering text prompt, or also using some memory bank. But of course, the using of the engineering prompts and memory banks is also, in a way, problematic in some cases, or not optimal. Another class of clip-based method is about the use of learnable prompts, and these learnable prompts also requires sometimes a generation of synthetic anomalies. So also in this case, it is not optimal. So what we want to introduce in this work is called a medclip, which is essentially a set of key characteristics. One characteristic is to introduce this dual branch architecture, and dual because we have a branch for the normal samples and a branch for abnormal samples. There is a vision language match. We don't use memory banks. We don't use, in a way, profiling of the normal data, but we just want to, in a way, adapt the language, the prompts to the visual data. Text is, in a way, not engineering. We are learning the prompts in some way using some a trick. Let's say we are we explain in a minute. And then we have also the use, for the first time, we use not the classical softmax loss used in clip, but a variant of this, which is called the siglip loss, which take into account some characteristics which are not useful using in clip. And then we have this dual optimization process to achieve a better class separation between normal and abnormal. Let's go to, this is the architecture. I want to just have a glimpse of this architecture. We have, okay, so this is working. So we have the visual encoder from the clip architecture and text encoder for the clip architecture, so pre-trained, if we have frozen parameters. And we have a set of adapters here, and the adapters are in a way combined in some way. And also we have the text coming here, so we have to match here and then the classification and the segmentation. So let me start with the input. We have this branch on the top is for normal. The other branch here is for abnormal. This is a VIT architecture. There are 24 layers. So we take the output of these layers at a certain point. We just subdivide the 24 layers of VIT in 4. So we have these 4 outputs from the vision, normal, abnormal. We provide the image level classification labels, which are balanced between the normal and abnormal. And we have, when available in the data, we use also the segmentation map. So, and the output is given in terms of classification score, here C, and the segmentation map M. Now, okay, so we have this learnable adapters. So the learnable adapters are, in a way, separate adapters for normal abnormal. So we have this AN and AB here, so different adapters. And what we want is essentially to leverage on the pre-trained knowledge of the clip training, but adapting to the medical part and to the task, to specific task. And in fact, we have this adapter, which are in a way have the task, have this goal to learn feature specialized for classification and segmentation, of course, before adapting. So we use a couple of layers for each adapter. One is using this format. It is essentially linear layer W, which is shared between all the adapters. Essentially, this is the task, the goal to adapt the natural pre-training to the medical domain. I is the output of the VIT of the vision encoder. And the second layer is divided in two heads. One is WDET and the other one is segmentation, which take in input the layer, the shared layer, and giving input to these other two values. After that, we have the text encoder. Text encoder we have used some description of normal abnormal, using also synonyms for that, don't just the two classes. V and W are essentially the learnable prompts. We put in an input text encoder to produce the final encoder. So these final encoders are essentially final prompts are essentially composed by the learnable prompts V and W, the classical in a way class prompts in normal abnormal, and the objective which take into account the anatomical part. So can be brain, can be liver, can be something else. And then we have the two branch vision adaptation. So what we essentially have in these modules, we just try to match the output of the adapters for the vision part O, which is taken from the normal branch or the abnormal branch. We essentially match with the dot product, which is a cosine similarity, with the text prompt Tn. And then this should be maximized, because what you want is to match the normal prompt, the prompts, the textual prompt of the normal sample and the vision descriptor to be as similar as possible, minus, so the difference between the cross reference, so the normal prompt of the vision and the text for abnormal. And so what we want to maximize this difference, which means we have to maximize the first term and to minimize as much as possible the second term. The same is done for the other branch, just leveraging the abnormal part, which is actually given by this formula. Okay, so in the end, we combine the two values here in a single, and then we predict after some other softmax operation anomaly score and anomaly map. The loss function is given as a summation of the Li. I is the layer which we take the features from the vision part. And these actually are three terms, the lambda hyperparameters which are taken unitary for in this work. And these three terms, the dice and focal losses, are essentially more used for the segmentation map, because they take into account better the boundaries between the normal and abnormal areas, for example, and given more weight to the difficult sample, which are just the ones, the pixels just close to the boundaries. And the seglip is this, in a way, loss, which is used essentially to consider independently the pair between the text prompt and the image, differently from the traditional clip loss, which take into account instead all the classes, and the results is dependent from also the other classes. In this case, seglip instead are calculating the similarity between the image text pairs independent of all the others. So this is actually the final part, the architectural part, and the experiment. Essentially, how many minutes I have? 2. Yes. Okay. Okay, so the experiment are in a way for the sake of last year, because this is a work of last year, was state of the art, in the sense that, okay, we used, first of all, a data set with 5 modalities, X-ray, OCT, histopathological images, MRI for the brain, and liver CT or another. And the results are in a supervised case here, and the few shot, which are the better. Our work is this one in the bottom. Okay, I don't want to discuss this OCT data because a little bit particular, but okay, let's assume that all the others, and you see also in the average, we are getting better results in average over all data set, and also refer to the state of the art, using just 2 samples per class. So 2 samples for a normal and abnormal, 4 or 8. So essentially, this few shot seems to work better. We have an ablation study, different ablation studies, in which we show that every missing of the stage, for example, while replacing the textual prompt without the anatomical part, but just putting genetic medical images, we have a drop in the classification and segmentation. We also try to reduce the number of adapters. We try to eliminate the difference between normal and abnormal in the loss in the in part of the architecture. And we have anyway, we demonstrate we have several drops. And sorry, okay, so and finally, also this architecture demonstrated to be also interesting in terms of transfer, essentially, because what we do is essentially having training on 16 samples from source data set, which is chest, brain, OCT, and rest. And the target was an unseen data set. And we see that we respect to the state of the art, previous state of the art, our MedClip work anyway reasonably better, sometimes much better than this one. And this is also an interesting part. So I'm concluded this. This is actually presented MedClip, which is actually leveraging the clip architecture for medical image anomaly detection. Of course, there are some limitations. The use of adapters and the prompts can be in a way make a little bit more fine and better. There is still this modality gap between images text, but anyway. And then we want to go towards zero shot and multimodal, so to leverage also the different modalities. Thanks for the attention and